Let us first establish some notation and conventions when we deal with 2D and 3D discrete signals. Let x n1 and 2 be a two-dimensional signal. n1 and 2 are the independent variables. They're integers. They take values 0, plus minus 1, plus minus 2. And mathematically speaking, a signal, an image, can have infinite support. That is, the values that n1 and 2 take are between minus infinity and plus infinity. When it comes to the orientation of the axis, I can use n1 as the horizontal axis and to the vertical one with this orientation. That's how we are used to representing functions in calculus. So here is 0, here is the point n minus 1, here is the point m minus 1. So this is an n by m image. So if this is n1 prime, this is n2 prime, then here is the pixel with coordinates n1 prime and 2 prime. The value of the pixel is, in general, a real number. Now, drawing from the way matrices are represented on the computer, I can pick the n1 axis this way and the n2 axis going like this. So in this case, if I pick the same n1 prime, it will be here, approximately here. The same n2 prime will be approximately here, and therefore this is now the pixel with coordinates n1 prime and 2 prime. Clearly, as long as the orientation of the axis is known, the result of processing an image should be identical. It shouldn't matter which way I have chosen to represent the axis. When I deal with color images, then there are 3 channels involved: the blue, the green, the red channel. If these channels are added up, I end up with a color image. So if this is the n1 axis and this is the n2 axis, again, the location, the n1 prime and 2 prime location of the pixel will be the same. The pixel is the same location, x, n1 prime and 2 prime. But the difference now from the previous cases is that x, n1 prime and 2 prime is now a vector, a 3 by 1 vector, where I have the value of the red channel at this location, followed by the value of the green channel at the same location, followed the value of the blue channel at the same location. Okay, so the RGB representation. So x, therefore, in the general representation can be a scalar or can be a vector. When I deal with 3-dimensional discrete signals, then x, n1, and 2, and 3 is the representation. n1 and 2 and 3 are integers. And again, mathematically speaking, they can range from minus infinity to plus infinity. So here is a collection of frames representing a video. So I can choose n1 going down this way, n2 is the second axis, and n3 is the third axis. It represents discrete values of the time domain. And now an x, n1 prime, and 2 prime, and 3 prime would be a pixel. Let's say if n3 prime is here, it will be a pixel in this frame with the other 2 coordinates, n1 prime and 2 prime. It's a bit hard to exactly represent in this case, but you do get the idea. Let us now talk about some specific signals that we will be making use of in this class. The first one is the unit impulse, we'll denote it by delta, n1 and 2, and by definition is equal to 1 when the arguments are equal to 0. So if I'm here on the 2D plane, here is N1, here is N2. Then I'll denote the delta like this, and the height of the delta equals 1. I can shift the delta around, so I can write delta N1 minus N1 prime, N2 minus N2 prime, and then according to the definition, it's equal to 1 as long as the arguments are equal to 0 and 0 otherwise. So from here we see that it's 0 when N1 equals N1 prime and N2 equals N2 prime. So again, if I'm to sketch it, depending on the values of N1 and 2, I have not restricted them. So let's say N1 prime is here and N2 prime is here. Therefore, in this case, I have a signal like this. So it's a delta, its value is 1, and it's 0 everywhere else on the plane. I can talk about a three-dimensional delta by introducing an N3 there. So the definition will extend to B1 when N1 equals N2 equals N3 equals 0. An interesting notion is the notion of separable signals. A signal G is separable if it can be written as F1, which is a function only of the one variable, N1, times a function F2, which is a function of the second variable only. The question then is whether the 2D delta is a separable signal, and the answer is yes. We can, let's look at it pictorially first, right? If I have a signal that looks like this, so it's a line of deltas. So it's 1 on the vertical axis and 0 everywhere else, and all these values are equal to 1, right? And then if I have a signal that has a line of impulses on the horizontal axis, so these solid dots here all have value of 1, and the signal is 0 everywhere else, right? So now if I multiply these two signals, then it should be clear by just these pictures I'm drawing here that I multiply, like this one is multiplied by 0 here, this one is multiplied by 0 over here, this one is multiplied by 0 at this location, and it's only this one here at the origin that is multiplied by 1 here, and therefore the result is just this signal, which of course we have defined it. This is delta N1 and 2. Now what is the first signal equal to? This is a delta N1, right? Because this is by definition equal to 1 when the argument is equal to 0 and 0 otherwise. But I'm on the two-dimensional plane, right? So delta N1 is 1 for N1 equals 0 and any value of N2, no restriction on N2. So therefore, N1 equals 0 on the vertical axis. N1 equals 0 here, N1 equals 0 here, 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 here. So this line of impulses, the first one is represented by this, mathematically by this function, delta N1, and similarly this line of impulses is a delta N2 signal. Therefore, delta N1 and 2 can be written as delta N1 times delta N2, and it is therefore separable according to the definition, right? So delta N1 takes the place of F1 N1 in the definition, right? So this, I'm rewriting the definition here, times F2 N2. Another useful function is the discrete unit step. it's denoted by u, and by definition it's equal to 1 as long as its arguments are non-negative. So n1 is greater or equal than 0, and 2 is greater or equal than 0. So if I'm to sketch it here, is again 1 as long as n1 is greater or equal than 0, but also n2 greater or equal than 0. So the values of the solid circles are 1, and then this signal extends from 0 to infinity in the n1 direction and 0 to infinity in the n2 direction. We often label the quadrants. This is the first quadrant, this is the second one, this is the third one, this is the fourth one, and in this case we say that the discrete unit step has support in the first quadrant. We can shift the unit step function around, so if I have n1 minus n1 prime, n2 minus n2 prime, then by definition this is equal to 1 as long as its arguments are non-negative. And 0 otherwise. So from here we see that n1 is greater or equal than n1 prime, and n2 is greater or equal than n2 prime. So if I'm to sketch this shifted step, depending on where n1 prime and n2 prime are located, so let's say n1 prime is here, and n2 prime is here, right? So then the shifted step function looks like this and extends to infinity this way, and to infinity this way. So this is the coordinates of this point is n1 prime, n2 prime. The next question is whether the unit step is separable, as was the delta, and the answer is yes. So un1 n2 can be written as un1 times un2, and pictorially un1 is 1 as long as n1 is greater or equal than 0. So it looks like this. Again, the solid circles have value 1, so it extends to infinity this way, and this way, and this way, right? So this is un1. un2 is the signal that is 1 as long as n2 is non-negative, so it will look like this. Right? So it extends this way, this way, this way to infinity. So this is un2. And clearly, if I multiply these two signals, then what I'll end up with is the unit step, right? So it's going to be non-zero only in the first quadrant. So this is un1